working as research assistant in Institute of Organic and Polymeric Materials and Research and Development Center of Smart Textile Technology in National Taipei University of Technology, Taiwan. And in this webinar, we are going to look upon next generation technology towards smart textiles. And first of all, we should know why we need smart textiles and how the textiles has evolved in the past, how the beginning is, and now the present stage, what it is going on, and what will be the future. So let's go into it. Okay. Yeah. In the beginning stage, the human civilization, we didn't wear any clothes, and to prevent our skin, so we started creating some cloths by natural materials like fiber based or natural leaf based, something like that. And the tribe people, they evolved with some weaving techniques, and then we formed some wrapped and weft, and then we formed some woven or non-woven structures. So yeah, we also use some silk cocoons, like plant-based as well as animal-based, derived, something like that. And the humans, they already know how to process the animal skin, their hides, to convert them into the leather form so that it can be stable. They do some chemical treatments using some toxicants, but now they are trying to overcome those things. That is different part. So we just focus on smart textiles, how it is evolving. Okay, now the next stage is and then the trend changes and people started preparing some synthetic materials in order to get some comfort zone. So what kind of comfort, if we are the users, what kind of comfort we will expect? For example, we should want some air permeability, or the moisture should be managed. If we are going to sweat, it should come out, and it should be breathable. So these are all the things we will consider. And it should be hydrophobic in terms of, if we want some anti-wettable characters, we should consider something like this. Or if we want some oleophilic, something to for example, if you want to separate some oil or water separation, this kind of things, we need some this kind of materials, like omniphobic, this kind of materials. So then the technology evolved one by one. In the past it was like this, and in the present it is growing, and now the trends have changed a lot, because everywhere we use textiles, like blanket, or for our insole or in socks. If we are going to use it for footwears, or in terms of leather, we also use some textiles as lining. To prevent the coatings, we use something like some other treatments to prevent the fibers. So now the technology has evolved so much. In the past it was like this. So the next stage is wearable electronics, because we are concerned about our skin and our body health. Now we are trying to communicate with that, how we can communicate our health with our textiles. And it is possible to transmit our details. For example, if we want to monitor our body's function, so we can easily monitor with the present technology. And we have already prepared this kind of, this is already in present stage, it is available, and it is commercial. Everyone is using some Apple watches, through which we can transmit our data wirelessly. So the technology is growing towards positive way. So in this case, you can see how they are monitoring the temperature, body temperature, or else they can also monitor something like human heartbeat or pulse rate, like this. So it is possible. And apart from the anti-wettable characters, they are also involving like storage. Energy storage is important, because in the present stage, we know that we are looking for some green energy, because many of the countries, they are relying on something like fossil fuels, and which is not recommendable, because which is creating a lot of pollution to the environment. So in order to avoid, we have to rely on something like green energy or circular economy. These are all needed, and it is demandable. So in this case, you can see the figures. We are using the fiber-based materials to store the energy, or we can create some platforms through which we can monitor. For example, if you are going to monitor your body motions using some fibrous materials like textiles, through which we can also try to communicate to the wireless medium using some yeah, communication port like Bluetooth or Wi-Fi, through which we can easily communicate, so that we can also monitor your activities like that. So the IoT is like that, and the present state, the cloud computing, all these things are encouraging those things. So it is easy to monitor. And yeah, these are all the papers they are discussing how they can monitor different motions, body motions. For example, if they want to stimulate your nerve cells, they can also use those things as a stimulant, using some textile based materials, because usually the thin film based materials, they are not air permeable, and they have some limitations because it is not otherable. So if we have this kind of textile fiber based materials, it is easy to evolve. So we are preferring to use fiber-based materials, especially textile-based. In this case, because the fiber-based, we know that initial stage is fiber, and then we can convert it to yarn, and then the next stage is textile, right? So yeah, there are many methods to prepare fibers, and we'll look upon it. And in this picture, you can see that here there are different patternings, because I already discussed what we are going to do with our wearable electronics. Because the wearable electronics, we know that if it is flat, it has some disadvantages, like you cannot achieve better performances. In order to achieve better performances, you should engineer the structures into a micro patterned or nano pattern structures. So there are different patterns here you can see. One is like serpentine structures, bridged islands, or kirigami patterned, or liquid metal infiltrants, or you can also pattern different things like mogul pattern. In our case, we are focusing on pattern fiber-based patterns. I'll discuss in the upcoming slides. And then, yeah, in this slide, I want to highlight the significance of renewable energy. Why we want to rely on renewable energy? Because yeah, in this figure you can see how the environmental pollution is caused. What are all the factors is governing these things? Because the global emission, CO2 emission, is mainly contributed by the power supply. So what we are relying on power supply is usually coal based, so which is going to create a lot of carbon dioxide emission to the environment, so which will create global warming. So in order to create awareness, most of them are switching to different sources like solar cell or wind energy, these things. But in terms of wearable devices, it is better to harvest the human body motions, because if we are going to use solar energy, we need some storage systems. For example, we need some batteries to store those energies and then utilize. For example, if you are going to work on the morning time and night time, if you want to use them, you need some storage system. But in this case, if we want to impregnate energy-based system based on our biomechanical motions, it can convert the energy from our body into the electrical energy then easily. We don't want to store the energy actually. If we want to do, we can also do using some batteries or capacitors, which is also growing, and I'll discuss in the next upcoming slides. And yeah, apart from that, there are some shortcomings in the wearable electronics, because there are many challenges, not only one or two, there are many. Especially it should be less weight, and the size should be very down to nanometers or micrometers to get the better performances and washability, or it should be thermally stable, or it should not have any interference. For example, if you want to monitor the heat body temperature something, it should not for example, if you're going to create some motion, it should not interfere in these things. So yeah, and the connectivity and how fast the device can perform. For example, if you want to monitor the human body motions, the response time should be rapid, because our motions are faster, right? So in order to monitor those, it is necessary to design a structure which is having better durability and reliability. So yeah, these are all the needs we need at the present stage. And yeah, wearable market growth. It is necessary that why we want to work on this field, because we should know the market trend. Because in the past, we know the fiber-based textiles are only reliant on something like this kind of application only for wearability. But now we are going to evolve into the next stage. So we also want to think upon different applications based on wearable electronics. So yeah, there are many opportunities. So yeah, it is recommendable. For example, if I want to start a new project, then I should think how it is possible, how it is feasible in the present stage, and how it will be evolved into the next stage in the upcoming future. The trend will be how much influential. And in this case, you can see these are all the datas, and here you can see the basic watches. The trend is not growing that fast, but when you compare to the smartwatch, everyone is switching to the smartwatches because they want to monitor their health, because people, they want to know how their health status is. So it is better, they don't want to go to the doctor and check all these things. It is good to have some haptic devices, tactile devices, which can be easily adhered to the body, so which we can easily monitor. That we don't want anyone support, we just use some data to connect with our devices, then it is easy, you can easily monitor every day. And whatever the data they are going to be collected, it can be also connected with the cloud, so it is easy to recover. You don't want to wait for until okay, you want to take out the memory card and transfer all your data. No need, it's very easy. So yeah, the clothing is also, you see there are many trends, for example, from watches, clothing, earwears. So everything is becoming wireless, and if you want to use something which is wireless, you should try to avoid something like, yeah, there are some complications between meeting this demand. So how to meet this demand by evolving with something like a wireless based system. So yeah, we look upon those things also if the time permits. And yeah, in this case, I'm highlighting the importance of wearable electronics. In the past, it was not that good, and in the present, it's growing faster, and especially based on electrospinning and nano generators, because energy is most important, and we need some self-powered devices. We don't want to supply energy to extract the data. We want something like self-powered. Whatever we are going to work out, it should be easily converted into the energy. Then that energy can be easily utilized in the form of yeah, electrical outputs. Yeah, in this case, you can see they are using some wearable LEDs. In this, you can see that can be stretched and flexed. And the other one is published in advanced size from our group. In this, we are trying to prepare some self-healable material, polymeric materials, because we know that the normal materials, whatever we use in our day-to-day life, which cannot be self-healed. But if we can self-heal, for example, we always inspired from the nature. Our human skin, if it got damaged, it can heal by itself. So the same way, if our electronics is going to get damaged or tampered by something, it can be healed after some time. And the challenge is it should be healed very fast. Then only you can keep monitoring your devices, right? So it is important task to do with. And another thing is not only the performance, as well as you have to control the self-healability time, and then the performances, as well as the mechanical strength, because mechanical strength is more important for the wearable devices. If it fails, there is no use of using the devices, right? And yeah, there are many health applications also, healthcare applications. For example, they want to monitor, or they can use something like if they want to supply the, if they want to monitor something like wound healing applications, for example, they want to check their antibacterial effects over some period and how the cell is going to respond. Those kind of things also they can monitor. Or if they want to stimulate the cells, they can do by using this kind of energy generators. And yeah, now we get into the fiber preparation methodology. There are different methods to prepare fibers, starting from melt blowing, centrifugal spinning or force spinning, blow spinning, laser assisted melt spinning, microfluidic electrospinning. So here I can just give a simple example how we prepare the fibers. We just put some polymers over here through the heating plate that can melt your fibers, and then it can push. And then using the spinneret, you can easily spin the fibers and then coil them and form as a yarn with the winder, with the help of winder. The same way, it's like preparing a cotton candy. In this case, the centrifugal or force spinning method is similar to preparing the cotton candy. If you have seen that, they just put some sugar in the middle and then they rotate at high speed, then it can create, the polymers. For example, sugar is also a polymer, right? Macromolecule. So it is going to, after some heating, it will try to melt, and then the polymer will flow. If you're going to use the centrifugal force, the polymer is going to spray everywhere. The polymer will be ultra fine. For example, it will be in micrometer or nanometer, depending on your parameters, whatever you are choosing. So we have to control those things like concentration or based on the speed, or yeah, like this kind of things, heating, this kind of things will influence your fiber output. So the dimension is also important because we need to control the diameters. Usually with the fibers, whatever we are using in a normal case, it's like in or micrometer, millimeter, or some possible case there are some micrometer based, micrometer sized fibers. Yeah, so now the advantage of using my technique is electrospinning. Because why we want electrospinning? Because we can fine tune the fiber morphology. We can get ultra small diameters, for example micro to nanometer range. It is possible to achieve with the electrospinning. So I'll explain those things, how it works, the electrospinning setup. Yeah, we'll look into those things. And there are different modifications they do with that. We can also see those things. Yeah, here, this is the basic setup. You can see they have a pump to pump your solution. Here in the syringe, we'll put some polymer solution, what we are decided for. For example, if you want to use some PVP or PVA, polyvinyl alcohol, some polymers, you just prepare the solution with a suitable solvent, and then you put them into, and then you apply some high voltage. That high voltage will drive your polymer molecules to flow through, because that will create, then you have a collector to collect those things. With the help of grounded collector, you can collect those fibers, and then that fibers can be utilized in the different way. So yeah, this is the basic setup. In order to get different morphology, or if you want to tune your morphology to core shell or hollow sheet structure, you can also make it by using different type of setup. For example, in this case, they don't have only one syringe, they have a two-way. Here you see there is one way, the other way is sheet structure. Core, this is the middle part is called core, and the outer layer can be considered as sheet solution. So if you want to prepare a gradient of polymers, for example, if you want to choose a polymer A and polymer B, and you can put in inner core is A, for example, and B, like if you want to prepare a core sheet structure, you can consider A or B or B or A in that way, so that you can create a core sheet structure. Or if you want to create some hollow structure, it is also possible, because if you are going to use some water soluble polymers inside your cores, then you can easily make them to etch with some water. Then you will end up with the hollow structures. It is very easy to work with. And yeah, you need to get expertise. Within few months, you can get expertise. It is possible to prepare, but you need to fine tune your parameters. For example, if you want to prepare polymeric nanofibers, you should consider several things I'll discuss. And I also published some recent articles based on that, and you can have a look on it. And in this case, we are using a grounded collector. There are different type of collectors. In the right end, you can see there are different type of collector types. Here you see the plate type, parallel plate, and the rotating drum, bed spinning type, because yeah, it depends on your methodology. If you want to create a specific, it depends on your specific needs. So you can optimize, you avail those things. So you can optimize and fine tune those things. And here you can see there are different kind of electrospinning setup. The basic setup, whatever we see in the page number 13, your slide number 13, you can see this is the basic setup. And if you want to create some different structures or different type of yarns, and if you want to improve your strength, you can choose different way. So yeah, there are different possibilities to alter your setup by using some insulating tape or steel blades here, so that the collection can be done, because we need some standard conductive collectors, because the polymer have to deposit on it. We have to connect some voltages to that conductor, so that it can establish the electric field that can drive your nanofiber or microfiber formation. So yeah, here you can check there are different varieties of electrospinning. If you are interested with, you can go through this manuscript. This is published very recently in Applied Materials Today. Yeah. And then nanofibers. Yeah. In our technique, we are using basic electrospinning setup, which is easy to work with. And this is how the setup looks like. Here you can see the polymer solution with the flow rate controller. With the pump, you can try to push your solution. Then it can be collected in your grounded collector. So there are different parameters. For example, you can see the polymer concentration, flow rate control, distance between the needle and the collector. It is important. If you want to tune your diameters, it is more important. And applied voltage, whatever voltage you are going to provide, that will also create some ultra fine nanofibers. Sometimes if you tune your voltage or if you tune your flow rate, you can get some exciting results. And we always try to avoid some beats, because in your fibers, we always want complete fibers. If you have beats, that may degrade your performance. For example, your strength will get degraded, or your optical emission. If you want to use some for optical property, it will create some agglomeration that will create big fluctuation in your results. There will be a big deviations in your results. So yeah, you can go through this article in which we are discussing about conjugated copolymers based electrospun nanofibers, and then we apply those conjugated electrospun nanofibers in different sensing application. For example, metal ion sensing or other toxicants, pH based sensing, or humidity sensing, temperature sensing, those things. You can have a look, and it is free to see because it is an open access journal, so everyone can have a look on it. And this is another article we published. This is also a review article. In this, we highlighted the importance of electrospinning, as well as we showed that how the normal, because the previous article is only related to the conjugated copolymers, and in this we discussed widely, we comprehensively discussed the whole part regarding the electrospinning, plus how the factors, what are all the factors going to influence, and traditional methods, what are all the setbacks and bottlenecks, and finally how they overcome those things using some electrospinning setup, nanofiber based sensors. So this is more important, because we know that when we go to the nanoparticle or nano dimension state, we can get better performances, because we can improve the surface area. That is more important, because most of the people, why they want to prefer using some nanoparticles, we need to achieve something higher surface area that will create a better catalytic area, catalytic sites, active sites, so that will improvise your sensing property. For example, if you want to sense some metal ions, if you're just going to use the thin film, the exposed area is very less. But if you're going to create some nanoparticles over your thin film, or if you're going to create nanofibers with nanoparticles, that may critically develop, or it may improvise to a very good extent. So that is what the basic mechanism of using some, why we want to rely on nanofiber structures. And then, this is the overall picture. You can see electrospinning is used widely in different fields, not only for the smart textiles, they're also employed in optoelectronics, energy harvesting, batteries, supercapacitors, food packaging, anti-fouling, biomedical applications, sensory applications. If you have time, you can just have a look on this article. And now I want to go with the functional materials, because we have already discussed what is called electrospinning, why we want to rely on electrospinning, what electrospinning is going to give us. And now we need some pillars to impregnate into our nanofibers, so that we can create some exciting results. For example, if you want to use some perovskites, if you are from material science background, it will be very well known to you, because if you are working on solar cell or light emitting diodes, definitely you might have heard about perovskites. So now I'll introduce a little bit basics about perovskites. What is perovskites? Perovskites is a normal mineral. And then why we need perovskites? Perovskites are cheaper when compared to other materials what we use in the conventional methodology, and then it is easy to process, and the preparation method we can easily fine tune. And most probably because the previous way what we prepared some semiconductors is just by vapor methods, vapor based methods. Now if we are going to employ this kind of mineral based perovskite materials, then it is possible to switch from vapor based to the solution based. Solution based techniques are encouraging, because we'll avoid a lot of energy outputs needed to make the vapors, and then we have to control those systems, and the systems are very expensive. If you want to overcome these things, you should rely on solution-based techniques. So yeah, the major advantage of using perovskites is the processability, and you can easily tune your perovskites. But the major disadvantage is that is not stable to the environment. If you are going to export to the air or humidity or temperature, it's going to degrade after a certain point. So what are all the factors which is going to govern your stability of your perovskites? So we look on those things. First of all, I like to introduce perovskites. The basic structure is ABX3. Here you can see the structure. A is a metal site. B is your lead or tin-based metal sites, and the X is your halide. Halides are, if you're from chemistry background, you might have heard about halogens, bromine, chlorine, fluorine, iodine, like those things. Yeah, we can tune. If you want to tune your color, you can tune this X site, then you can easily fine tune your colors. And the major setback of previous inorganic quantum dots are their color purity. If you check organic emitters and inorganic quantum dots, whatever they used in the past, it's having some problem with the color purity, because here, if you check the PL emission, it is wide. If you want to get a very good color quality, you should have a narrow FW channel, full width half maximum. If your this peak, PL peak is very narrow, you can control your color easily. So the perovskites, importance of perovskite is the processability, color tunability, and their color purity. So yeah, next stage is in this article they have discussed why the instability occurs in the perovskite, and what are all the methods to overcome those stability by using some polymeric encapsulation or inorganic encapsulation, or some silicates they use to encapsulate not only polymers, they also use some inorganic materials to bind the perovskite, and then they can protect the perovskites inside the matrix. So yeah, and then apart from that, they also can fine tune the structures, because usually in the beginning stage, they only can prepare 3D perovskites, and then they gradually evolve to 2D, 1D, and 0D structures. Yeah, then they can improvise the stability to a greater extent, so that we can improve the durability of the device. Yeah, and then here, why the stability is affected? Because the structure get collapsed. The main reason for the stability is the structure. For example, if you want to use your function material, for example, if you want to charge your mobile, you should have the proper port to insert. That structure is suitable for this, so the charging will be happening. The same way, if you want to harvest the energy, or if you want to extract the light from your perovskite, you should have the proper structure. That is more important. So how to tune your structure? By choosing a specific cations or anions. So how to choose your cations or anions to prepare different perovskites? They in this article, they have said how to control your tolerance factor. And what is called tolerance factor? The formula is here. You can see the radius of your, in this case, you can consider MA is your A site, B site, and X site, ABX3. In the beginning, I say perovskite have a basic structure called ABX3. So if you can control A, B, so you can control your tolerance factor. So if you control this tolerance factor and octahedral factor to 1, then you can get a better stability. In this picture, it is clearly, it can be clearly visible. See here, for example, if they change different cations like sodium, potassium, rubidium, cesium, like this, they can control their tolerance factor. If your tolerance factor is within this range, 0.8 to 1 means you can have a better stability. If your tolerance factor is too high, or if it is too low, the perovskite will easily degrade. So that's why we rely on cesium-based perovskites, because in our project, we always rely on inorganic cesium-based perovskites, because most of them are having better tolerance factor. This is the major criteria for your stability. And in this case, you can see how the metal halide based perovskite light emitting diodes have given different color tunability. Here, this colorful picture is called CIE coordinates. If you want to extract different light emission from different perovskites, because if you tune your halide section, for example, here you see they have chlorine, bromine, and iodine. If you have a chlorine in your excite, you will get bluish color. If you can tune your chlorine to bromine, you will end up with the green to yellow in this region. If you tune your bromine to iodine with that ratios, in between this ratio, you can fine tune your band gaps. Because we know that if we are from electrical background or chemical or material science background, it is important that we should notice the band gap is the major criteria for the semiconducting property. Perovskites comes under the semiconducting material. And in this case, why the perovskites is going to give different colors with the different halides. In this case, if you are going to tune your halides from chloride, bromide, and iodide, it's going to alter your work function. Then you will get a different band gaps with the different halides, so that you will get different color output. Because we know that if you have a band gap, you will have two different bands. One is called the valence band and conduction band. If you are going to give some energy as your, for example, if you are going to create some LED, you are going to give some electricity to your device, semiconductor. So that semiconductor will absorb the energy and it will excite. And then after some time, it try to come back. When it's going to jump back to your initial state, that time it's going to give out your energy in the form of radiative recombination. If this exciton, for example, you are considering this electron is going to move from this state to that state, that time electron and hole will form some excitons. That excitons is going to give radiative or non-radiative recombinations. Depending on your radiative recombination rate, you will get better electrical output. For example, in my case, if I'm going to create some LED, I'll just look upon radiative recombination rates. If the radiative recombination is good, means you will harvest better light outputs. So here, there are different preparatory methods. Here, there are, you can see they have a different precursor, AX plus PBX type. Here, we need two type of precursor, one step process. In this, we are doing like this. And the other step is two-step process. We do in a stepwise methodology. And then other one is nanocrystalline pinning. In that, we can, try to pin the nanocrystals. Then you can have a very good, smooth, uniform morphology. So because in terms of the electrical output, for example, if you want to create some solar cell or LED, the major thing is you should control your morphology. If your surface is good, you will get better outputs. So how can you fine tune your morphology? By controlling your nanocrystal formation by using some additives. We can look upon those things in the upcoming slides. And there are different methods, not only solution based, they also use some vapor based techniques. And the other one is, if you want to control your perovskites from 3D to 2D or 1D or 0D structure, you have to tune your ligands. Because if you have already seen how the nanoparticles have been synthesized, they use some ligands to control your nanoparticles growth, so that it won't grow further and it won't form the bulk particles. So in order to avoid the bulk particle formation, we always control with some ligands, big chain ligands. So if you are going to use this kind of hot injection method, in this we'll use some oleic acid or oleamine additives to control that can function as your solvent and ligands. Then it can control your perovskite growth so that you can achieve 0D structure, which is interesting. That can end up with the perovskite quantum dots. We know that quantum dots is very trendy material because most of them, they have already evolved to nanoparticles and nanofibers. And then the other thing is now 0D structure. So that is quantum dot. Quantum dot structures are necessary because we need better stability and better durability. So in order to achieve those things, we should confine our morphological characters and structures. This is more important. And apart from that, there are other methodologies using some microwave or ultrasonication or anti-solvent methodology. Yeah, if you are interested, you can go with some review articles. In that, they might have given more clear details due to the time restrictions. I'll go upon with the next slides. And here you can see I said how the LED is going to work. For example, you have an anode and cathode, two electrode system, and in between, you can see one is a hole injection layer and electron injection layer, and in the middle you have a emissive layer. That emissive layer, I'm considering this to prepare some light emitting device. In this case, I'm going to use emissive layer. Okay, emissive layer is going to emit your light. So how you are going to emit your light? You are going to inject some current using your anode and cathodes, through which your holes and electrons will go inside your emissive layer. You can alter your electron and hole mobility by using some hole injection intermediate layers or electron injection intermediate layers. So we need some additional layers to control the electron and hole mobility. So yeah, if you can control this mobility, you can achieve better efficiency. So that's what the idea of using some intermediate layers. Or otherwise, we just only rely on anode and cathode. In between, you put some emissive layer like perovskites. So yeah, here you can you might have aware of Jablonski diagram. In that, they have given how the absorption is going to take place, and the excited state, from excited state, how the singlet and triplet formation is going to occur, why the fluorescence is happening. We know that fluorescence, why it's going to come out from your material, because it's going to absorb. First of all, the basic criteria is your material should absorb something, and the absorption is going to get, after absorption, is going to excite. After excitation, it's going to come back to its normal state. During that state, it's going to give out the energy. That is what simply given in this Jablonski diagram. If it is the degradation is gradual, then it is called phosphorescence. If it is faster, then it is known to be a fluorescence. Okay. Yeah. And in this picture, you can see what are all the factors is going to govern your LED light emitting diodes performance. First thing is morphological control, and the other one is control of your charge. For example, electron and hole charge balance. It has to be balanced. If it is imbalanced, then it is going to damage your intermediate layers. So that will make your device to fail easily. So that will disrupt your device. So other one is you can use some nano membrane morphology. You can control your middle layer. For example, if you want to engineer your crystals within your particular confinement, if you want to create a nano grains or micro grains, it depends on your application. If you are going to apply for solar cells, they'll depend on differently. If you are going to use some LED based, they will depend on different kind of crystallization process. Yeah, so the crystallization process, we have to control it. It is very rapid. So how to control? By using some additives. So yeah, you can go further with this kind of articles to read more about this. And then, yeah, and stability governing strategies. Here, again, the Jablonski diagram is simply denoted here. One VB is called valence band, and the conduction band, excitation, and PL emission. If you have a defects, for example, if your morphology have many defects, the perovskite, why we are considering morphology again and again? Because if they have some defects or traps in your surface of your perovskite, that will induce non-radiative recombination. Non-radiative recombination is not good for your emission property. If you want to increase your emission, you want to rely on radiative recombination. How to improve your radiative recombination? You should improve your nanomorphology, morphological structures. You should confine your nanoparticle grains or quantum dots. You have to control your morphologies. So this is what highlighted in this article. And the other one is here. You can see the performance of perovskites and why the perovskites is growing very rapidly in the past few years. because of their performance. Here you can see organic LEDs, they are achieving very slow rate of achievements up to 30% EQE. But in case of quantum dot LEDs, it's growing faster. In terms of perovskite LED, it's even more rapid, and they have a very good FWHM. You can see the comparison between this and this. In this case, FWHM is only 30 nanometers. In this case, it's even more smaller. It is confined within 20 nanometers. That means your color purity is getting enhanced to a, it's enhanced almost like doubled. So it's very good for your application. So that's why we are focusing on perovskite materials. And what are all the strategies we need to consider if you want to improve your stability of the perovskite material? We should consider these factors. One is cation size. You can control your A site, and then you can also control your B site by using some, because we know that lead is going to be a toxic material which will affect the environment. So they're also working on tin-based or bismuth-based, that kind of materials. In the future, we can expect better outcomes with those materials too. Because the problem is, if we are going to replace the lead with other bismuth or tin, the sizes are different. So we will get some instability in the device, or the efficiency won't be that good as what we have achieved with the lead-based. And active materials, dimensional aspects. I said that we have different dimension, 3D, 2D, 1D, 0D structures. So we have to confine our structures. And fillers and its interaction, that is more important. How we can fine-tune the material by choosing the proper interaction between the perovskite and what additive we are going to add, and fine-tuning your morphology and controlling your work functions of your intermediate layers or your perovskites. This is published by our group, and in this case we are trying to use, this is the basic architecture. You can see ITO is the anode, and P.PSS is your hole injection layer, and this one CES-PB-BR3 is your perovskite, one type of perovskite. In this, we are going to put some additives like PEO. PEO is a polymer, commercial polymer, polyethylene oxide, and we choose that polymer. And then we add some other additive, dual additive, so that we can fine-tune the crystals of your perovskite formation. Here, the FESEM, you can see how the how was the influence of your PEO polymer and TPBA. So if you can alter these things, for example, if you can look at this table, you are able to see the table here. There are drastic growth in your luminescence. Lmax is nothing but your luminescence, light output, how much light, how effectively it's going to glow. For example, in your luminescence, you can see only perovskites without any additives, it's only 300. When we are going to fine-tune our structures, here you can see the FESEM image. Here, this is only perovskite, figure 8. When we are going to tune our PEO ratio and TPBA ratio, we can control the morphology, which is going to give you a better light emission, which is shown in the inset. You can also see your PL emission and EL emission here. This is our performance in this project we got. And the other project we also do to optimize our morphological characters by using some other polymer called PVP, polyvinyl pyrrolidine. In that, we also use some interlayer between the P.PSS and perovskite, because we know that P.PSS is also a semiconducting material and it is hygroscopic. We know that perovskite is not stable towards moisture, but P.PSS already have DI water in it, because the solvent they disperse with the P.PSS is dispersed in the DI water already. We do annealing, but still it's hygroscopic, so it will affect the perovskite. Then the layer is going to get affected, so that you won't get better performance. So we try to modify the P.PSS structure by using some PVP interlayer, polyvinyl pyrrolidine polymer structures in between, by tuning the structures. For example, we tune our structure within 5 nanometers in this range, so that we can optimize the thickness. Here with the cross-sectional image, if you can look up with the figure E, in this figure, you are able to see the cross-section. It is visible that PVP interlayer, PVP IL is nothing but interlayer we use. between P.PSS and perovskite. So if we are going to use this kind of PVP interlayer, which is going to make the interface assisted grain control process. We term this as interface assisted grain control process. We know that perovskites have to be confined into a smaller dimension to improve its stability. So if we use this kind of polymeric matrix, which smoothens the P.PSS, if you can see the structure, this P.PSS layer, you can see it's very rough. When we are going to use some polymeric interlayers, which smoothens the surface, so that if you are going to put your perovskites and form something filling by using some spin coater, we can fine-tune our perovskite structures within 50 to 100 nanometers so that we can achieve better results, and we have defect-free surfaces, which is what's schematically given here. You can see this figure with the different colors, which is here, A is only perovskites. When we are going to use perovskites with the PVP, it's going to alter your surface characteristics. And when we employ further with the PVP interlayer, we can harvest even more better efficiencies. So this is published in 2020. And this is how the mechanism works, because usually there are many defect states you consider. In this case, you can see there are defects in the perovskite emission layer. If we are going to use some PVP interlayer here, which can confine your perovskites in a particular matrix so that you can improve your perovskite stability, as well as the performance is getting elevated to a certain extent. So interface assistance is more important for the perovskites performance. And the other paper, which is published in ACS Applied Materials in the same year, we also work on stretchable light emitters. In this case, we are using polyurethane because we know that polyurethane having better stability, thermal stability as well as mechanical stability. It has very good durability as well. So we first characterize the PU electrode by using some silver nanoparticles and P.PSS with PUO. So here you can see the fabrication process. We start with the substrate with PU with the spin coating method. We know spin coating can achieve very thin layers, right? So we can optimize the condition of our polymeric stretchable matrix. So then we can use some silver nanowires, which is a conductive part. We know silver is going to be a conductive electrode. So we use PU with silver nanowires, which can be stretched, and it won't lose your percolation threshold. Okay, and then if you are going to implement a PVP interlayer in this, so you can also achieve a better results, which is also verified with this project. In this case, we are using dual polymers. One is PUO and PVP as well, so that we can control our morphological characters. Here you can see with P.PSS PVP plus PUO plus PVP. Here you can see the device performances with the different architecture. For example, here you see this is under 0% strain, 20, 40, and 60, 80, 100, up to 100%. The device is performing, but the luminescence degrade to a certain extent. But this is actually a good outcome. So in future, we can also develop further to improvise strain insensitive devices like that. So yeah, you can see these are all the confirmation for the perovskites formation. One is like XRD UV visible PL studies to see the absorption peaks and the emission peaks to cross-check the perovskite formation. Those things you can look upon. And the EDS image is also showing the perovskites formation, perovskites elemental mapping. And here you can see the durability of the touch responsive device. Here we are preparing some touch responsive device by using the architecture with some spacers in between. We use some PET spacers. So the electrode, if you are going to touch, the electrode can establish the contact between the layers. That contact can transmit your electrons and hold the injection will start, then the LED can glow. So this is the performance. You can see the touch responsiveness. And we also test the durability of our LED device under different fluxions with the wrench or some holders. We bend them and we check those things. Yeah. And this is another paper published in chemical engineering very recently by our group. And in this, we are confining the perovskites in 2D structures by using some ligands called PEA, polyethylamine. So yeah, we tune the structures from different, for example, in this case, we are using zinc bromide addition to control the structure. Here from the scheme, it is yeah, more visible. You can see if we are going to use zinc bromide with the different percentage from 0.1, 0.2, 0.4, we can actually tune our perovskites. And with this one, GIVOX, we can also prove which forms the 2D structures. And the other one is, this is the device performance. You can see we got better performances in terms of EQE and luminescence, because the previous works we just focus on green light emitting diodes. In this case, we work on blue light emitting diodes, because blue light is also very challenging. Blue light, because we know that we are going to change your halides, which will change your composition. That might create a different structure. That structure is not stable as green. So the blue is even more challenging. So we take up this challenge and we try to achieve some better results, and we got some good progress. And this is another paper. In this, we are using light emitting diodes by fine tuning the silver and short alkyl ligands, because usually when we prepare hot injection method, in the beginning, I say there are different preparation methods. In this case, we prepare the quantum dots 0D structures using the hot injection method by using 3 different ligands. One is, yeah, here you can see the different ligands what we use: conventional OA and DDAB and TOP. In normal case, we always use OA and OAM, oleic acid and oleic amine. And other case, we also want to compare the conventional structures with our desired targeted structures. So we compare different ligands like OA, OM, and DDAB and TOP. With that, we are able to say TOP plus silver is going to give a better performances, because we can tune the morphology, which is clearly visible here. You can see the quantum dot structures. Here you can see the d-spacing values also. We can confine the particles within 20 to 10 nanometers in this quantum dot range, quantum dot particle size range. Here, device operational stability is also given, because we are using ligands to protect our perovskites. So we can improvise the stability. So in order to prove we got a better stable perovskites, we try to demonstrate by using different solvents, because perovskites will degrade in polar solvents like water. So we try to demonstrate with the different solvents ranging from toluene to DMF. Yeah. And this is the device performance. You can see with the different FWHM, depending on your different ligands, like D is DDAP, T is TOP, and AGTOP is AG. It is shortly given in this form. You can go through this. And now we move from LEDs to sensors. This is another part we focus on, because this is also a part of research of our group. And this is published in Polymers in 2021. And in this, you can see the different working mechanism. Here you can see the dark blue boundary, which is upon strain, which can create some cracks, which is given schematically here. Or if you are going to use some nanowires, upon straining your surface, it's going to break your percolation threshold, so that your resistance will get higher. Because usually what we use, our conductors are going to have lower resistance, higher conductivity. If you have this kind of conductive structures which can be stretched, usually what conductors we use in our real day-to-day life is common copper tape or aluminum foil or something as our conductive material. In our case, we are tuning the conducting structures by using some polymers which can be flexed or stretched, those things with some conductive structures like silver or copper or some other conducting particles based on conducting polymers or something. So in this case, we are discussing different kind of mechanism, how it works. For example, ex situ or in situ nanofibers. These are all the fiber mechanism I given here. You can go through. And depending on these are all the tensile form. You can see tensile, we know that if we are going to stretch, this is tensile. Compression is different, tensile is different. So the pressure sensing or strain sensing is little bit different. So here you can see different kind of sensory modes. One is capacitance based or resistance based or piezoelectric based or triboelectric based. There are different pressure sensing modes. So these are all the things we have discussed in this article. This is open access, so anyone can access. You can go through this. And this schematic can help you to understand how the strain sensors usually work, resistive sensor, for example. Because I said, if we want to create a conductive material, we use some conductive particles. For example, in this case, they use silver precursor. You can see that initially they use some thermoplastic polyurethane, TPU. So they form the electrospun nanofibers, and then they use CNT with silver precursors so that they can form hybrids. So these hybrids, upon stretching, you can see the connections are getting disrupted. So this will break your percolation threshold. So in this form, you can see this is a schematic here, the real-time images they have captured with the FESEM. You can see the conductive particles is getting apart depending on your strain percentage. So depending upon your strain percentage, for example, if you want to use this kind of structure on your body, if you're going to work out or something, the body muscles are going to create the strains. Depending upon your strains, the peaks, the resistance will vary so that you can easily monitor your body motions. This is how the basic mechanism for your wearable devices, how the sensory applications have been done. And this one is another one, which is nature inspired. Here they have shown some scorpion structures, the same kind of micro wrinkles. Here they achieved by synthetic methods. Then upon straining, here you can see how the straining is influencing your wrinkles. Because if you have some wrinkles upon straining, the wrinkles is going to become flat gradually. So that is what they have shown here with the FEM, finite elemental analysis method they use to check this. They cross-check and verified with their real-time FESEM image. Here they have shown their performances as well. You can go through this manuscript. These and all, they are using it for wearable studies. And here, this is another paper. They have already used some PU multifilaments. We know that PU multifilaments, they got some commercial materials, and then they form some graphene particles, which is naturally inspired. You can see it looks like a worm. So this is worm-shaped graphene microlayers they formed. So yeah, they have demonstrated this kind of interconnects, or yeah, they want to create some stretchable interconnects like that. Usually they do. Or if they want to expand, they can do some wearable sensors like this. Or if they want to sense, the pressure, they can use. Based on the nature inspiration, they do different kind of application, because what our human skin is going to respond depending on the different stimuli. If we are going to strain, you can feel it. Or if you are going to touch the pressure, you can feel it. The same way, our electronics or wearables can feel whatever we are experiencing. The textiles can also experience. This is how it works. And this is my recent project. In this, we are trying to compare different structures, because in the past they have used different structures to achieve better stability for the wearable device. In our case, we are expertise in preparing some electrospun nanofibers. So we try to form the patterns with the electrospun patterns electrodes. So here, this is the basic scheme, how we prepare. First, I start with electrospinning and then use some conventional PDMS, which is commercial one. So we just put that material and then anneal and we peel and then wash out our PVA material. Because here I choose PVA because it's water soluble and it is non-toxic and it is easy to work with. So we can get nano patterns there because we have a lot of nanofibers. I can show you the FESEM in the upcoming slides. And if you pre-strain and you form some silver particles, nanoparticles on your conductive membranes, then if you leave, it will form some wrinkle structures like this. This is how the basic mechanism for the preparation of conductive electrodes. So here you can see ranging from A to I showed different nanofiber density. Here you can see different fibers I formed, which is in the range of 400 to 600 nanometers in this range. So I can easily take them out and form this kind of trench structures. Here you can see formation of skin-inspired micro nanostructures. You can see our human skin. It has a lot of micro wrinkles plus this kind of trenches, nano trenches, which is similar to this kind of electrode. So I inspired from our human skin, and then that kind of what substrate I make is visible. It's transparent, so it is easy to impregnate onto the human skin. It won't easily show up with your skin, so it is good to work with. And then I formed some silver trifluoroacetic acid to form some silver nanoparticles, and I conform with the FTIR peaks. And then I want to confirm the surface energy difference between normal flat surface, because usually they use flat surface to form this kind of electrodes. Why we want the pattern structures? Because this kind of patterns is going to increase your surface energy. This kind of surface energy influence is more important to get a better crystallization that will create a good adhesion between the structures, the substrate and the conductive layers. So which is shown in these peaks. Here you can see the exadic crystallization peak, and we also monitor the sheet resistance versus transmittance for the different electrodes. And then we check the FESM cross section for the different timings, because we want to, if we want to process something, we should look upon how to tune our timing, because if we have a very big processing time, it's not easy to process, right? So you should make it rapid. If you want to prepare some material, or if you want to prepare some devices, it should not take 2 days or 3 days to complete. It is rapid. Within half an hour, you can complete the whole process if you want to do this process. So it is advantageous to work with this. And I also check the stability towards different stretchings. So if you want to test your device for the wearability, we have to check this kind of flexion or stretching or twisting that may affect your electrodes. So I test those things for the different stretch cycles, for example, 0 to 1000. In the normal flat structure, within 1000, the performance is getting degraded. But in terms of pattern structures, I can achieve better durability and reliability. Here you can see the FEM analysis, simulation analysis, through which we can confirm why the performance is getting enhanced. So other one is we also check the IV curve and the sheet resistance with the different respective tensile strain. And we do some simulation study to check the validity of these prepared electrodes. And then with that, we also want to know whether our body wearable electronics will affect our body cells. So I also do some cell viability test, which is giving encouraging results. And then we also develop the project towards checking some antibacterial test. So it is also having antibacterial effect, because we know that silver nanoparticles have better antibacterial activity. So I just cross-checked, and strength-wise, it is having better strength when compared to other nanostructures, because which is having silver nanoparticles which can reinforce and make the structures more stable. So that is what happens. And I also check the real-time application for creating sensory application. For example, if you want to check the hand or finger motion, muscle motion, or when you are going to speak, or if you want to modulate your voice, for example, if you want to speak faster, how the sensory response will be, or if you are in the normal mode, if you're not excited, how you will speak. So it will vary depending on your electrode response. You can easily monitor the person's anxiety, like those things. And then I also checked some pressure sensory application, because we are expertise in preparing nanofibers. So I prepare some SBS based styrene butadiene styrene, which is stretchable polymer. We form electrospun nanofibers over our pattern structure, and then stack one more to get a sandwich structure. If you are going to apply some pressure, we can fine tune the density of our SBS structure. For example, SBS1, SBS2, SBS3, I prepared 3 different thicknesses so that I can optimize my sensitivity. I do those things. and I also check the strain intensity performances. And apart from that, I also do some flexible devices, light emitting diodes and ACEL devices, alternating current electroluminescence studies. With that, we can prove that it is working under different fluxes. So the prepared electrode, the patterned electrodes work finer than the conventional flat structures. So I proved with this, and it is published in ACS Applied Materials in this year. And I'd like to introduce to the another one, because in the beginning, I'm highlighting the importance of green energy, why we want to rely on green energy and wearable devices. We don't want to rely on some global warming issues. So we are going to eradicate those things by relying on this kind of small outputs, whatever we can achieve, we can extract from our human body motions. Yeah. Here, there are many skin-inspired structures or nature-inspired structures you can go through. And how the triboelectric works, because many of us are very aware that if you're going to create some stress on the material, which is going to give some electrical output, which is called piezoelectricity. The same way, if you are going to create two different potential material, for example, one is positive, the other one is negative. If you are going to create some frictions, that is already well known, because if you put your some different potential materials towards your hair, it is going to respond. It is going to create some electrostatic induction. The same way, our wearable devices can also work. So we try to demonstrate those things. And in the previous project, I also say these are all other review papers you can go through if you have time. And this is depending on the roughness, how the performances will vary, depending on the pattern structures, how the triboelectricity is going to influence your performances. Those things have been studied. And this is my project. In this, we are preparing some smart textiles based on nanofibers. So in this, we prepare two different kind of nanofibers. One is NCF, nanoconductive fiber. The other one is CNCF, coated nanoconductive fibers. Here, we are preparing with a different percentage of PTFE PU, because we know that the triboelectric series is given here in this slide. You can see one is positive and the one is negative. If the separation is good, means you can achieve better electrical output. You can gain more energy from that, so you can extract more energy. So depending on that conditions, we choose compatible polymers to work with. So we use some conventional easy method to dip coat them and form some fibers, and then we twist them and stretch. Depending on the stretch frictions, it's going to create the positive electric, positive negative, which is going to create triboelectric performances. So which is already noticed in our project, and we got some light output. It is fascinating for us. And then recently, we also do some piezoelectric study. We know that piezoelectricity is somewhat little different from triboelectricity. In this, we are going to create the stress. The crystals are going to, because we know that non-centrocentric materials, which is having different polarity, so the dipole moment will change if you're going to apply. So the polarization will change. Depending on the polarization switch, the voltage will also transfer, the electron will keep flowing. So depending on that, we use some conventional PVDF material to form some nanofibers using some electrospinning techniques. And then we blend some perovskites, because we already work on perovskites for the light emission. Here we are going to use the perovskites for the energy harvesting application. So it is exciting for us. And then we got some good beta phase formation using the perovskite quantum dots. And the perovskite quantum dots, we use the conventional method to form using hot injection. And then we use quantum dots with some CNC that will prevent the perovskite instability. So that we can get a better durability for our energy harvesting application. Here we have demonstrated the piezoelectric application. Here you can see the performances is around 25 voltage we can achieve. And we also check with the PNG and PPNG. PNG is the control sample. Here we are getting only 3 voltage for the PVDF conventional. But if you are going to blend perovskites quantum dots into your piezoelectric PVDF polymer, which is going to enhance your beta phase. That beta phase enhancement is important for the energy harvesting. So we get better voltage outputs. That is what noticed here. And then we also monitored with the different motions. For example, we also use it in the mask to see the breathing rate, which is going to create the stress. If you are going to breathe faster, it's going to create more stress on your material so that you can get higher output. So you can easily monitor your breathing rate, something like this. So we proved that, and we also checked the durability after 60 days. We checked in the beginning for 60 minutes, and after 60 days we checked because we know that perovskite may degrade. So we have to cross check this so that we can prove our perovskite can be used for a long time. So it won't degrade. It may degrade, but up to 2 months it's stable. And this is another paper we published based on this one, piezoelectric. In this, we are using electrospun reinforced structure by using electrospinning based on stretchable material plus silver nano precursors. And then here we are comparing two different structures. One is wet spun structure. Wet spun is nothing but it's a flat structure, flat fiber. Electrospun is interconnected. Here you can see the figure B. It is very obvious that it has interpenetrating networks of nanofibers. And then here in the zoomed inset image, you can see a lot of silver nanoparticles embedded in between the nanofiber structure. So this may act as a good reinforcement. For example, if you want to build a good home, what materials you rely on? You want to create some reinforcement with some steel rods, with some cements and your bricks. The same way, the architecture here, the nano architecture we are following, we are not only focusing on the microfibers, we focus on the nanostructures and how we can tune the interaction between nanofibers and nanoparticles so that we can get better interaction. How to tune those things we did stepwise. And yeah, everything is clearly mentioned in the paper. If you are interested, you can go through this paper, and we apply it for wearable gloves application. Yeah, here we also given some video demonstration. I didn't add in this due to the time restriction. Sorry for that. And then we also check the tensile strength measurements for the WS. Here, WCF is wet spun structure, which is conventional way. ERCF is important because we need reinforcement so that we can improve the strength and we can improve the durability of the wearable devices. So that's what here mentioned here. And here you can see the bending durability for 10,000 cycles we did, and it is stable. And we try to impregnate this kind of fibers into the real-time system, and we can also sew into our fabrics. So it is exciting. So upon sewing, we also check the stability. The deviation is very less, so it's good for the real-time application. And we check the FEM analysis. So here you can see the distinction between WCF and ERCF. WCF have higher strain over the sheet structure. Here you can see the silver nanoparticles on the top. So if you are having higher stress, it's going to degrade anyway, right? So if you can adjust your stress by using this kind of electrospun reinforced structure, you can dissipate the energy so that you can retain your performance for a longer time. That's what given here. So, and also we check the straining durability. We did for nearly 6,000 cycles. For the ERCF, it's stable, whereas WCF within 700, 800 cycles, it's getting higher. That means the durability of the device is not appreciable for the wet spun structures. So we also check the stability towards saline systems, and then ultrasonication, and then we also tried for water, ethanol, those things. We added those data into it. And then this is the nano generator application, because we are going to use this kind of system, electrospun reinforced conductive fibers with PVDF structures. So PVDF, we already see in the previous project, we have already demonstrated PVDF with perovskite, how it is getting enhanced, the voltage outputs. In this case, we are going to check the normal WCF structure and ERCF structure. Based on that, we have given the name called the WSNG and ESNG. ESNG is having the better output, so that yeah, it is applicable to get the energy output. So the videos are available in the article, so you can have a look on it, how the energy is getting generated depending on the tapping. Yeah, so we do those things. And yeah, these are all the papers I published in the recent years. So if you are interested, you can go through one by one. And if you have any doubts, you can just contact me via different platforms. I'm available in Google Scholar, ResearchGate, and other platforms too. So yeah, or you can ask Professor Kiran Kumar, who's the organizer who invited me. I want to thank him. And here, I'd like to share the references or whatever I'm speaking about. You can just look about these things. And yeah, this is my research platform. You can go through this links. I have also attached the QR code. If you want, you can just scan and you try to contact me via either Google Scholar or ResearchGate or ORCID. There are many. You can just follow me. Yeah, thank you for your patience listening. And here, I'd like to introduce the Taiwan because I'm in Taiwan for the last 5 to 6 years. So yeah, these are all the natural beauty of Taiwan. You can also experience if you have any time. If you have any work related to Taiwan, you can try to visit. And I'd be happy to see you in Taiwan. And these are all the places. This is National National Scenic Spot. This is called Yangmingshan. Yangmingshan is a national forest area. Here we have a lot of forest resource. You can go for hiking. You have waterfall. You have hot spring. Everything available. You can have some friends and you can have a tour with them. Or if you have any queries regarding to the tour, you can also ask me. I can guide in my own way. Whatever I have experienced, I can share it with you personally. And traditionally wise, I can say they follow some Taoism, which is like Hinduism, Christian. There are many, right? The same way they have traditional people here. They follow this kind of tradition. I take some recent pictures. I want to share it with you. They have this kind of tradition. Yeah, they go in this kind of costumes and they worship the god. They have some stories behind. And I'd like to thank my team, Professor Ko. He is in the middle. He is my professor, Professor Dr. Chichin Ko, and these are all my teammates. And I'd like to thank him at this moment. And yeah, this is my university campus. If you'd like to see my university website, you can just log into this website, and they have different scholarship for the international and local students. You can have a look. If you are interested, you can apply during spring or fall semester. They have regular intakes. You can just Google and check. You'll be able to know all these details, or else you can contact me. And and my collaborators are these people. I want to thank all those collaborators. They always help me and they have good support for me. And I would like to thank all the organizing committee people here, and especially Professor Kiran Kumar, who gave an initiative to hold the lecture for, I'm interested to present based on smart textiles because I have a pretty decent interest, and I also have explored different things, and future will be even more interesting. By the way, I'd like to thank all the audience, and I congratulate all for your patient listening, and you will be having your bright future. Yeah, thank you one and all. Thank you. Yeah, if you have any questions, I'm open for the questions. Yes.